In this video, I want to talk about combinations. Now, these drastically oppose the kind of calculations that we've been doing in permutation. Permutations revolved around a lot of countdown calculations. The counting principle, for example, had a lot of multiplications, how many options are available. We could condense that into a factorial, which represents this whole countdown. And there was literally a 5p5, for example, button that meant you were calculating a permutation. 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 However, in the land of combinations, things are quite different. Now, in a combination, we want to really just stick to this calculation, NCR. And I don't get to go into too much detail, especially in Math 30-2, about all of the mathematics behind a combination. We don't really spend a lot of time going really into the little details. That's more Math 30-1 territory. But I do want to talk about the vast difference, the huge canyon that kind of separates these two calculations once you really do look at it carefully. And getting these mixed up eventually does seem kind of silly because they're so different. Now, let me just create something really small. Let me talk about, oops. Here are 4 options, a sample space of 4. Now, if I was to build a story where arranging these options created something new, like a password, and said, hey, let's build passwords out of those 4 options, out of those 4 letters, then it would kind of make sense that anytime you switch stuff around, anytime you reorder it, anytime you rearrange it, it creates something that would actually be a totally different password. And in that scenario, we have all these. This is literally what we would call a permutation. And a permutation, for me, one of the most meaningful definitions of a permutation, shown exactly what I'm just doing here on the left, is when rearranging creates new outcomes. If you were moving anything, move anything, and if it changes the password, if it changes the way people are lining up in a photograph, if it does in fact change what you're looking at and what you've created called an outcome, you are building yourself a permutation. And that is where, you could use the counting principle, 4 times 3 times 2 times 1. You could use the factorial, 4 factorial, and you could use your permutation, known as 4p4, to come up with all of the codes possible. There are 24 different codes possible in that scenario. However, if I was to create a different story, and in this story, moving these around doesn't change anything. Well, that doesn't change anything. Like a salad. And these are ingredients. And maybe you're putting avocado and bacon or kale. I know kale spelled with the C or the K. Don't judge me. Or something that goes in a salad starting with a D. And maybe these were 4 ingredients in a salad. Now, good luck moving stuff around to try and make it more delicious. You can move anything around. You can switch your avocado with your cucumber, or whatever that C means, and all of a sudden you can't say, well, that's a different salad. I rearranged it. Well, that's just nonsense. And we create a story where quite literally rearranging does not, vastly opposite, polar opposite, a complement, does not create new outcomes. And if rearranging seems to be completely futile, a waste of time in the story we've created, well, my friends, you are working on a combination question. And a combination definitely has a much smaller amount of outcomes. In fact, if you were to go try to say from 4 ingredients, we are merely selecting, but not arranging, merely selecting all 4 of those ingredients. Well, you can try and move them around all day, or you're just creating one salad. And these combination calculations are significantly smaller than say all the different slightly, every little rearrangement creates like a new password or something. That's why these permutations got so big. But we have this combination calculation which works for situations which 100% don't respond to moving this around. There's the common phrase out there that people kind of, a lot of teachers kind of teach, that say order matters versus order does not matter. Not my favorite way to kind of visualize or understand the difference. I think the whole rearrangement scenario, whether it works or doesn't, makes it much clearer as to kind of what you're working with. So let me kind of create a classic combination example. Let's say we have 4 girls, we have 7 boys, and we have 2 teachers. We need to create a yearbook committee. And we need this yearbook committee to have 4 students and 1 teacher. This would be my first kind of problem here. How many ways could this happen? Now, the idea is that if you picked 4 students, I mean, if you picked your 4 students and you picked the teacher, well, what's it going to matter if you just start rearranging these people? How could you convince me that if the teacher is picked first and then the students are picked after, that's somehow a different committee? That's going to be a different group of people who are making different decisions? I feel like this is identical to this. Now, we're not saying someone's in charge. I'm not saying that one person is the president and the next person is the secretary. And yeah, switching positions definitely would change like the order and the seniority and the responsibilities. Sure, that's not what we're talking about. We're just picking a group of people. Who's coming? Who's coming to the meeting? And whoever shows up first is not going to change the meeting. So that should, in theory, that's a duplicate. If you select different people, yeah, totally different combination. But in every combination, moving people around will not matter. So we don't want to, what would be a terrible choice is to accidentally pull out the fundamental counting principle and to set it up like this and say, well, there's 11 people and 11 students. And 11 students, or you could pick from 11 people first. And then there'd be 10, and then there'd be 9, and then there'd be 8. And then for the teacher, there would be 2 choices. Because unfortunately, what you've done is created a permutation of 4 people and then a permutation of the teacher, which is going to give you a much higher answer than if you said from 11 people, we're taking the combination of 4 people to pick the students, and then multiply. From the 2 teachers, we're choosing 1. That is the money. And so just to contrast, with the wrong permutation strategy, 11 times 10 times 9 times 8 times 2 would give you up to 15,840. Whereas 11 choose 4 multiplied by 2 choose 1. Come on, typo. Only comes out to 660. And for me, that's right. This is a combination story, a committee of people where everyone is equal. Wouldn't matter if you move people around. Rearranging them ain't going to do a thing. Now, we can put slight restrictions into these kind of questions. Let's say, well, we can't just take any of the students. We got to make it quite more, maybe a little bit more equitable. So we have to make sure that there are 2 girls selected and 2 boys selected and 1 teacher. And then maybe we have to make sure that our combinations are balanced and that there's girls and boys and a teacher. And so in these cases, picking the girls, picking the boys, picking the teacher all create their own combinations. The word and is an important connector. Remember logic, and versus or. This is an and. We get to multiply these combinations together. And now I would say from the 4 girls, we're selecting 2. From the 7 boys, we're selecting 2. And from the 2 teachers, we're selecting 1. Where 4 choose 2 comes out to 6. 7 choose 2 comes out to 21. This comes out to 2. And 6 times 21 times 2 tells us that there would only be 252 different committees where there was exactly a balance of girls, 2 boys, 2 girls, and the 1 teacher who would say supervise this committee. So here's an introduction into what is the difference. Why do we do combination calculations sometimes? And a very, very classic example, a committee kind of calculation. And what to avoid. Don't do that. Not for a combination. Thank you.